So, we have branch instruction. Now, all branches in case of ARM processor, so they are relative to the program counter. So, previously we have seen that there are different types of branch. So, one classification was absolute versus relative branch. So, in absolute branch, so the target address was specified directly. So, the branching was to that particular address, and the relative branch means it is with respect to the program counter. So, instruction will have an offset value, that offset value will be added with the program counter, and whatever be the result, so the control will jump to that particular address. So, this is useful because it will help us in program relocation. So, that we have seen previously, and this jump is always within a limit of plus minus 32 MB. So, so it is not the entire address range, but plus minus 32 MB. Conditional branches you can make by having this condition codes, like say branch is the simple branch is B, now you can have say EQB, like say for branch on equality, like that. So, you can have the condition codes part of it. Subroutine call is also a variant of branch instruction. So, we will have two opcodes, one is the B, which is the standard branch instruction, and the other one is BL, which is the branch with link. So, subroutine call, the difference is that the PC plus 4 value should be saved in the link register. So, if you use this BL instruction, this BL instruction will save PC plus 4 into this register R14, and so BL can also, so this can be used for subroutine call. And return for subroutine, so there is no return instruction. So, you can just have this R14 copied back into R15. So, it is coming back from the subroutine. So, we can use that. So, the branch instruction format is interesting. So, we have got this first most significant 4 bits. So, they will correspond to the condition code, then this 101. So, this is the opcode for branch, and then this L bit. So, L is the link bit. So, it is 0 for branch and 1 for branch with link. So, this is this 0 and 1. So, the branch and branch with link B and BL instructions, and then the offset part. So, this will tell the offset by which you want to jump. Now, you see that I have said that in the previous instruction, previous slide, that this is sorry, we have said that this branch is plus minus 32 MB. So, plus minus 32 MB if you want to go. So, how much total space is total is 64 MB. So, 64 MB means, so this is MB is 20 bits and this 64 is 6 bits. So, total 26 bits of offset will be necessary. So, in 26 bits of offset, so you can jump from minus 2 power 26 to 2 power 26 minus 1. So, so many space, so much of space, that is plus minus 32 MB. Now, if we are doing that, so you can sorry, this is 25 to 25 minus 1. So, if you want to do that, then this 26 bit has to be stored. Now, this offset part we have got space for only 24 bits. So, bit 0 to 23. So, for that matter, so this 26 bit difference will be calculated, but the offset value that we have is only 24 bit. Now, why is it like this? So, you see that if you look into this ARM instructions, so these ARM instructions are all 32 bit wide. So, it is 4 byte wide. So, if you look into the memory map, the instructions when it is put into the memory, so it will be like this. The first instruction will be at location 0, 0, 1, 2 and 3. So, they will have the first instruction, then the location 4 will have the second instruction, 4, 5, 6 and 7. They will have the second instruction, then location 8 will have the third instruction. So, it will go like this. So, this is the first instruction, this is the second instruction, this is the third instruction. So, it goes like that. So, what I want to mean is that you do not need to jump in between. Okay. So, whenever you are jumping onto a particular location, so you are jumping at the beginning of an instruction, and all these addresses 0, 4, 8 etc. If you if you look into their binary representation, then the least significant 2 bits are always 0. So, these 2 bits are always 0. So, there is no point when you are taking the difference between the PC and this the jump target. So, this least significant 2 bit results are always 0. So, there is no point storing those zeros separately. So, what is done for this offset calculation purpose, we first compute the 26 bit difference between the branch instruction and target, and then we right shift the value by 2 bits. So, that these two zeros will go out, and these least significant 2 bits are so they are always 0. So, they will go out. As a result, from this 26 bit you will get the 24 bit, and this 24 bit will be stored with the instruction, and during execution. So, you will get this 24 bit offset value, and that 24 bit offset value will be left shifted by 2 bits to get 26 bit offset value, and that will be sign extended to 32 bits, and then it will be added to the program counter for branch target. So, this way this branch operation will take place, and it will be taking care of this. So, this space optimized version you can say. So, in one instruction, so entire effort is made to fit the instruction in one memory word, 32 bit word. So, that it is done like that. So, next we will look into another important instruction, which is known as the swap instruction. So, swap instruction is an atomic operation in which memory read is followed by a memory write. So, if you look into other operations of any of this ARM processor memory operation, so it is either a memory read operation or a memory write operation, but it is never the same. But as far as the OS design is concerned, so whenever we are going for implementing some synchronization primitives like semaphore, monitor, mutex, etc., or some locking mechanism, we need to check the content of a memory location and set it to some value in the same instruction. So, what is required is it is like this. Suppose I have in a program, so there are there is a memory location whose name is say flag, and there are two programs. So, program P1 and program P2. Both of them want to modify a portion of the memory. So, it wants to modify, they want to modify this portion of the memory. Now, naturally, if both of them modify simultaneously, then the content will be lost. So, what these OS designers provide is you can have some sort of flag like this. So, you can set this flag to 1, and when this processor 1 comes, so it check process 1 comes, the program 1 comes. So, it checks the flag, finds that it is 1, maybe it is allowed. So, what this program will do? So, it will put it to 0 and go into this modification, and after modification it will revert it back to 1. And when the value is 0, if P2 comes, so it will find that the value is 0. So, P2 will know that it is not free. So, it will wait until the value becomes 1, and when the value becomes 1, then possibly P2 will put it to 0 again and then proceed. So, this is a very standard protocol that is followed in the synchronization between processes. Now, the difficulty is that when P1 is checking the value of flag, so it has to do it at a very within a very short amount of time, and it should not be interrupted in between. So, I can the P1's code, if I write like this, it may be like this, that read flag into register R1 if R1 equal to 0, go to L1, where L1 is this instruction itself, reading the reading the register content. Else you set R1 equal to 1 and store R1 to flag. So, if I say that my arithmetic operations in an arithmetic operation, I cannot save the content, you cannot use memory location. So, then you have to write the code like this, where this reading is one instruction, then this condition check is another instruction, this setting is another instruction, and this saving is another instruction. So, total 4 instructions will be there. So, what can happen is that a number of read write operations, one memory read and one memory write. So, they are needed for doing this whole operation, and since they are two different operations, so interrupt can come in between, and that interrupting routine, so it can do some modification to the flag. So, that way it may be the content may become inconsistent. So, somehow I need a technique by which this read and write they are done simultaneously. Okay. So, almost all the processors you will find some technique by which you can do it. For example, if you look into say the 8085 processor, you remember that there is an instruction like XTHL, where the stack top content is exchanged with the HL register pair. In a, so that is so these two contents are exchanged. So, in a single instruction, so we are exchanging the stack top with HL, or so that way it is, or say SPHL instruction. So, in a single instruction we are exchanging this pair. Why is it so important to exchange in a single instruction? Because that will avoid inconsistency into the values of those registers. But ARM, so far we have seen that it is not doing that, it is having a load store architecture. So, in an instruction you can either load from memory or you can store into the memory. So, this swap instruction is the only instruction by which you can do this load and store simultaneously in a single instruction. So, the format is like this: is the swap, read, swap, then read RD, RM and RN. So, I will just this diagram explains it better. So, this RD, RM and RN, these registers are mentioned. So, the first operation is from the memory location which is pointed to by the RN register, the value will be moving to the temporary register. Then secondly, this value of this RM register will be put into this memory location, and finally, content of this temporary register will go to RD. Now, if the RM and RD they happen to be the same register. So, if this RM is say RM equal to R1 and the RD is also equal to R1, and this memory location content is say M, okay, and RN is some other register, suppose this is the R2 register which is just a pointer. So, after the first operation this temp will be equal to M. After the second operation this M will get the content of R1, and after the third operation this RD will get the content of M equal to RD will get the value of temp. So, that is M. So, what has happened effectively is that this R1 register and this memory location content they have got exchanged. So, after this whole thing is over, this memory location has got the content of R1 and R1 has got the content of memory location. So, this way in a single instruction I can swap between the two memory location and register, provided these two are same. So, this is written here. So, we can it is a 2 cycle operation. Content of memory location pointed to by register Rn is copied into temporary space, then the register Rm is copied onto the memory location, and finally, content of temporary space is copied onto register Rd. So, if Rd and Rm are same, in that case there will be an interchange of the content. Okay. So, this is the utility of swap instruction, and this is very much useful for the OS designers. Then modification of the status registers like the CPSR and SPSR register. So, this can be done only in the privileged mode, not in the user mode. So, there is an instruction like MSR that moves content from the CPSR or SPSR register to selected general purpose register. So, you can get it onto a general purpose register, and then you can access that general purpose register to check the content. And MRS it is doing just the reverse. So, content of the general purpose register is copied onto CPSR or SPSR register, and it can be executed only in the privileged mode. So, this way we can modify the status registers in the privileged mode of operation. So, so far whatever instructions we have discussed about, so they are all ARM instructions. So, we can have thumb instructions, as we said that thumb is 16 bit instruction set. So, unlike ARM which is 32 bit, so this is 16 bit. So, they are stored in a compressed form. So, in per memory word, so in memory word is 32 bit. So, per memory word, so you have got two such thumb instructions. So, I should say that this thumb instruction set is more close to the standard microcontroller instructions. So, they are executed unconditionally. So, there is nothing like EQ add or say LE sub like that. So, you can have only add sub type of instructions, and only the branch instructions are conditional, but excepting that all other instructions they are unconditional. Then they have got unlimited access to registers R0 to R7 only and R13 to R15. So, R8 to R14, so they are not R8 to R12. So, those registers are not accessible in the user mode. The reduced number of instructions will access the full register set. MRS and MSR type of instructions are not available. Maximum SWI calls limited to 256. So, we are back to the convention that the Intel processors have. They have got INT, the software interrupts number 256. So, when you go to the thumb mode, so it has got only 256 SWI calls. Then the instructions look more like conventional processors instruction, like push pop instructions are back now. Okay. So, you can have this push and pop instructions, and on reset or exception, this ARM the instruction set activated is the ARM instruction set, and if you want to switch from ARM mode to thumb mode, so you can use this BX or BLX type of instruction. So, BX will be branch with exchange of instruction set, and BLX is basically the call with exchange of instruction set. Similarly, when you are executing the thumb instruction set, there you can put a BX to come back to the ARM mode of execution. So, instruction set is ARM instruction set in that case. So, this BX and BLX, these instructions can be used. So, if you just want to compare between this ARM and thumb, so it is like this. The similarity wise, both ARM and thumb, so they are load store architecture. They will support both will support 8, 16 and 32 bits of data, and the memory model that is used is 32 bit unsegmented memory. So, entire memory space is similar. Okay. So, we do not have differentiation, like this is true for some Intel processors, where the memory is divided into code segment, data segment, stack segment like that. But in case of both ARM and thumb, it is taken as a unsegmented memory. So, it is the responsibility lies with the programmer to have the understanding as program memory or data memory like that. As far as differences are concerned, conditional execution is supported in ARM, but it is not there in thumb. So, ARM in general has 3 address format, whereas thumb has 2 address format. Okay. So, again that is the destination and source first operand, they are same. So, it will be going back to the conventional instruction style. Then thumb has less regular instruction format. So, the instruction format will be not that regular like ARM, and it has explicit shift opcodes like that. In case of ARM, you remember that we have got this LSL part, but the modifier was put along with the opcode, like say we have got say add, we had instructions like say add R1, R2, R3, and then we said the LSL by 2 bits. So, it was that R3 was left shifted by 2 bits. So, that shifting was part of the instruction itself, but in case of thumb, so there is a this shifting is separate. So, first of all you have to do a shift left R3, and then only you can say add R2, R3, telling that R2 gets content of R2 plus R3. So, these are 2 operand instructions mostly. So, that will be the format. Now, other differences and similarities are like this. So, this is the instruction execution. ARM execution is faster. So, if you have got this 16 bit thumb code, so it goes to the instruction pipeline and then it goes to a thumb decompressor. Okay. So, So, this decompressor will convert this ARM instruction thumb instruction into ARM instruction, and that goes to the ARM instruction decoder. So, the processor does not execute thumb instruction directly, it executes ARM instruction only. So, that way this requires some extra overhead. Okay. The thumb instruction execution will be slower compared to the ARM instruction. So, this is the way conceptually you can see that from the data memory it comes. So, if it is an instruction, so it will enter into the instruction pipeline. If it is a data, it will go to the data, it will come as data in and it will go to the B operand bus. So, B operand bus, you remember that was a part of the ALU. ALU was getting A bus and B bus. So, this is the B bus. Now, if it is an instruction, it goes to the instruction pipeline. Now, so we can have this select high or low half word. So, 16 bit are selected. So, it is going to the thumb decompressor. So, for thumb instruction. So, this is consisting of two instructions now. So, one instruction is the higher order 16 bit and other one is the lower order 16 bit. So, this multiplexer, through this multiplexer, so it will select the instruction and that will go to the thumb decompressor. Or if it is a simple ARM mode, then this part does not have any meaning. So, the instruction 32 bit instruction comes to this multiplexer and then it will be going to the ARM instruction decoder. Or it is from the thumb decompressor. So, the thumb instruction that we have got here is converted into 32 bit ARM instruction and that goes to this multiplexer, and ultimately the 32 bit is coming as output, and out of the 32 bit some portion is the opcode. So, that will go to the instruction decoder part, and some portion is maybe the immediate data. So, immediate field. So, that immediate field will go to the B bus finally. So, if the immediate part is there, then it will be, so it will get that immediate field will get that value. If the immediate part is not there, then of course, this instruction decoder will generate various control signals for doing the operations. So, why should we go for thumb? Like apparently it seems that okay, it is slower than ARM, but why should we still go for the thumb instruction set? First of all, the code density is higher. Code density, we have said that if you have a computation a function, then the so if you write down the corresponding program, then how many bytes are needed for holding that program. So, that is a measure of the code density. The thumb code on an average requires 30% less space. So, these are all statistical in data. So, it is not true in general. Okay. So, if you take any arbitrary program, so this will not hold, this may not hold, but in statistically it has been seen that it requires 30% less space. And if memory is organized as 32 bit word, then the ARM code is 40% faster than thumb. So, that is a huge speed improvement. So, ARM will be running much faster. And as far as thumb is concerned, so thumb is if it is organized as 16 bit word, then the thumb code is 45% faster than ARM. Why this thing happens? Because when the memory is organized as 32 bit word, in each memory access the processor gets one ARM instruction. So, that way it is executing, whereas it gets two thumb instructions, but they are to be passed through the decompressor. So, that way it will be slowing down. On the other hand, if you are having 16 bit memory word, then for getting a 32 bit instruction ARM instruction, so you need to access memory twice. So, that way the memory access time, and particularly if the memory is off chip, then this memory access time will increase. So, this thumb code will now be faster, because every access will give it one instruction and that it can go for execution. So, thumb code will be faster. But the major advantage of thumb is that it consumes 30% less power than ARM code. Okay. So, that is a huge advantage, because these ARM processors, they are meant for this power saving, and you can see that they are using thumb instructions. So, you can have 30% less power consumption. So, that is one thing that we will look for. So, this is the suggestion, like for best performance we should use 32 bit memory and ARM instruction set. So, whenever we are looking for performance of the system, that is the delay of the system will be minimum. So, in that case we should go for 32 bit memory organization and go for ARM instruction set, because that will make the system fast. On the other hand, if you are looking for best cost and power efficiency, then we should go for 16 bit memory with thumb code, because now this power will be less, power consumption will be less, and this 16 bit memory. So, this memory bus size and all those things will be less. So, this power so cost of the system will come down. Okay. So, cost the memory space required will be less. So, the cost of the system will come down. So, if you are looking into an embedded application, then in an embedded application, so all tasks are not equally critical. So, there are certain tasks which are very critical and certain tasks which are not so. So, for the critical tasks, so the major emphasis there is to optimize the execution time, and for that purpose we should use 32 bit on chip memory for speed critical routines. Okay. So, as you know that ARM core is there. So, along with that we can put some memory core and synthesize the whole thing together, fine. So, the memory since it is made on chip, so I cannot make that memory very large, but I can put some small the most important jobs of the application, most important tasks of the application into that memory, on chip memory, and use them. I use the ARM instruction set for their coding, so that it will be executed faster. On the other hand, this thumb code, so there are less important operations of the system. So, I can use off chip memory, and store the program for that non critical task onto that external memory, and this they can be coded in the thumb code, because now that will take less space. Okay. Now, though it is the program may be large, but because of this coding, the thumb coding, the program size will be small. Okay. So, that way this for embedded applications, so we need to use both this ARM and thumb instruction sets. ARM instruction sets will be for critical operations, and thumb instruction set will be for non critical operations.